Hello and welcome to the lesson on estimating a population mean. In the last section we found population proportion confidence intervals, and population proportions are usually found when we're looking at categorical data. When estimating a population mean, we need to collect quantitative data. It makes sense to try to estimate the mean amount of sleep that students at a large high school got last night, but not their mean eye color. When we know the population standard deviation, we can run what's called a one-sample z-interval for the population mean. To do a one-sample z-interval for a population mean, we will draw a simple random sample of size n from a population with an unknown mean but a known standard deviation. As long as the normal and independent conditions are met, a confidence interval for the population mean can be found using this equation: the sample mean plus or minus the z-score times the standard deviation divided by the square root of n, the sample size. This method isn't very useful in practice, however. In most real-world settings, if we don't know the population mean, then we don't know the population standard deviation either. But we can use the one-sample z-interval for a population mean to estimate the sample size needed to achieve a specified margin of error. Choosing a sample size for a desired margin of error when estimating. A wise user of statistics never plans data collection without planning the inference at the same time. We can arrange to have both high confidence and a small margin of error by taking enough observations. The margin of error, ME, of the confidence interval for the population mean, U, is... So to determine the sample size from a desired margin of error, we'll substitute the value for Z for your desired confidence level. We'll use a reasonable estimate for the population standard deviation from a similar study. Then we'll set the expression for ME less than or equal to the specified margin of error and solve for N. When we do not know what the population standard deviation is, we'll use t-distributions. When the sampling distributions of the sample mean is close to normal, we can find probabilities involving the sample mean by standardizing. The z-score equals the sample mean minus the population mean divided by the population standard deviation divided by the square root of the sample size. Now, if we have to use the sample standard deviation, we'll show a much greater spread, and the statistic t equals the sample mean minus the population mean divided by the standard deviation of our sample divided by square root of our sample size. It's called a t-distribution. It has a different shape than the standard normal curve. It's still symmetric with a single peak at 0, but with much more areas in its tails. The statistic t has the same interpretation as any standardized statistic. It says how far the sample mean is from the population mean in standard deviations. We specify a particular t-distribution by giving its degrees of freedom. So we will draw a simple random sample of size n from a large population that has a normal distribution with a population mean and standard deviation. The statistic will be t equals the sample mean minus the population mean divided by the standard deviation of our sample divided by the square root of our sample size. And that has a t-distribution. The degrees of freedom will be n minus 1. There are 3 things you need to know when we're comparing t-distributions to normal distributions. Density curves are similar in shape with t-distributions and normal distributions. They're both symmetric about 0, single-peaked, and bell-shaped. The spread of t-distributions are a bit greater. They have more probability in the tails and less in the center than the normal distributions. This is due to using the sample standard deviation rather than the population standard deviation, which brings more variation into the statistic. And as the degrees of freedom increase, the t-density curve approaches the normal curve. This happens because the sample standard deviation oops, hang on a minute, the sample standard deviation estimates, we'll put right in here, the population standard deviation more accurately as the sample size increases. Now we're going to discuss constructing a confidence interval for the population mean. We'll start with the standard error. The standard error of the sample mean will be the sample standard deviation divided by the square root of the sample size n. Now, what does this do? The standard error describes how far our sample mean will be from the actual population mean, on average in repeated simple random samples of size n. To construct a confidence interval, we will replace the standard deviation, which is the population standard deviation divided by square root of n, by the mean of its standard error. We'll use critical values from the t-distribution with n-1 degrees of freedom in place of the z critical values. That is, the statistic plus or minus the critical value times the standard deviation will equal the sample mean plus or minus the t-score times the sample standard deviation divided by the square root of our sample size. Remember from before when we were calculating the confidence intervals for population proportions, the same three conditions must be met to find the confidence interval of sample means, meaning they must be random, independent, and normal. So again, the conditions for inference about a population mean. The first one, random. The data must come from a random sample or a randomized experiment. It must have a normal distribution. Population has a normal distribution and a sample size has to be large. In this case, the sample size has to be greater than or equal to 30. And 3, it's independent. The individual observations are independent. When we sample without replacement from a finite population, we should check the 10% condition to verify that the sample is no more than, no more than 1/10 of the population. Using t-procedures wisely. The stated confidence level of one sample t-interval for the population mean is exactly correct when the population distribution is exactly normal. But no population of real data is exactly normal. The usefulness of a t-procedure in practice, therefore, depends on how strongly they are affected by the lack of normality. Procedures that are not strongly affected when a condition for using them is violated are called robust. Again, robust is an inference procedure that the probability calculations remain fairly accurate when a condition for using the procedures is violated. This is important, write this down. If outliers are present in the sample, then the population may not be normal. The t-procedures are not robust against outliers. Why? Because the sample mean and the standard deviation of the sample are not resistant to outliers. Now, when should we use a one-sample t-procedure? We can use a one-sample procedure if the sample size is less than 15, but only under the condition that the data appears normal and there's no outliers and it's clearly not skewed. Now, if the sample size is at least 15, we can use one-sample t-procedures except in the presence of outliers or strongly skewed. And with large samples, this procedure can be used even if strongly skewed, as long as the sample size is equal to or greater than 30. This will conclude our lesson on building confidence intervals for sample means. Going back to the beginning of the year when I told you you needed 4 dividers for your binder, and one of those was going to be for AP exam common errors, or AP tips. Well, I'm going to start giving you the AP tips verbally, and they're going to be bonus questions on your note quizzes. We're going to go all the way back to Chapter 1, a common AP exam error. When students are asked to describe a distribution on the AP exam, many students only comment on the shape. To get full credit, they need to address shape, center, spread, and any outliers. Remember the acronym SOCS, S-O-C-S. This will help you on the exam. Make sure to copy down this common error into your notes. Again, thank you for joining me for the lesson on sample mean confidence intervals. And give a little shout out to our March birthdays, Mr. Charlie Keegan and Miss Tricia Singh. Happy birthday, fellow Piscinians.